Beneath the Swiss Alps, beneath glaciers, beneath rivers, beneath mountains that took millions of years to form, there is a tunnel. Not a short tunnel, not a modest tunnel. A tunnel that stretches 35.5 miles through solid rock. The longest railway tunnel ever built on the surface of this planet. And at its deepest point, 1.4 miles of mountain pressing down from above. That's nearly 7,500 feet of rock, ice, and geological pressure bearing down on a structure built by human hands. For 17 years, engineers and workers drilled, blasted, and bored through the heart of the Alps. They encountered underground rivers, pressurized rock that exploded outward when punctured, temperatures inside the mountain reaching 115 degrees Fahrenheit. 2 workers died, dozens were seriously injured, and the cost, $12.5 billion, made it the most expensive railway project in Swiss history. But when the Gotthard Base Tunnel opened in 2016, it didn't just set records. It changed the way the world thinks about what tunnels can be. This is the story of how Switzerland drilled through the roof of Europe. To understand why Switzerland built this tunnel, you first have to understand what the Alps mean for Europe. The Alps are not just a mountain range. They are the spine of the European continent, a 750-mile barrier of rock and ice running from southern France through Switzerland, northern Italy, Austria, and into Slovenia. For centuries, the Alps divided Europe economically and culturally. Goods moving between northern and southern Europe had to cross mountain passes, dangerous, seasonal, and slow. In winter, many passes closed entirely. Entire trading routes shut down for months. Switzerland sits directly in the center of this barrier. A landlocked nation of 8.5 million people, strategically positioned between Germany to the north and Italy to the south. Almost everything moving between northern Europe and the Mediterranean has to cross Swiss territory. By the late 20th century, that traffic had become a crisis. Freight trucks by the tens of thousands were crossing the Alps every day, through mountain passes, through older tunnels, through small alpine villages that were being slowly suffocated by diesel exhaust and noise. Switzerland had a choice: build more roads, accommodate more trucks, let the Alps become a highway, or do something that had never been attempted before. Move the trucks off the road entirely, put them on trains, and drill a tunnel so deep and so direct through the heart of the Alps that it would make rail freight faster than road, for the first time in European history. The idea of a base tunnel through the Gotthard Massif had been discussed in Switzerland since the 1940s. Not a mountain tunnel, the kind that winds up through alpine passes before plunging into the rock near the summit. Those already existed. The Gotthard Road Tunnel, opened in 1980, was one of the longest in the world. A base tunnel, a tunnel drilled at the base of the mountains, at valley level, cutting through 35 miles of solid rock in an essentially straight, flat line. The engineering advantages were enormous. A flat tunnel means trains don't have to climb. Trains that don't climb can carry far more weight, move far faster, and consume far less energy than trains grinding up mountain grades. The economic case was clear. The engineering challenge was almost incomprehensible. The Gotthard Massif, the mountain block through which the tunnel would pass, is not uniform rock. It contains multiple different geological formations, each with different properties, different pressures, different groundwater levels, different temperatures. Some sections contain hard granite that would destroy drill bits in hours. Other sections contain soft schist that could collapse without warning. Some zones had underground water under extreme pressure, capable of flooding a tunnel section in minutes. And at 1.4 miles of overburden, the rock pressing down from above, the pressure on the tunnel walls would be unlike anything engineers had dealt with before. In 1992, Switzerland held a national referendum on whether to build it. The Swiss people voted yes, by 64%. Construction began in 1996. The primary tool for boring the Gotthard Base Tunnel was a machine so large it barely seems real. A tunnel boring machine, a TBM. The TBMs used on the Gotthard were among the largest ever built. Each one measured over 400 meters long, longer than 4 football fields placed end to end. Each one weighed over 3,000 tons. Each one required a crew of around 40 people operating simultaneously to function. At the front of each TBM was a rotating cutter head, a circular disc of hardened steel teeth, approximately 9 meters in diameter. As the head rotated, the teeth pressed against the rock face with enormous force, up to 265,000 kilonewtons of thrust, grinding the rock away at rates of up to 40 meters per day in ideal conditions. Behind the cutter head, a continuous conveyor system carried the excavated rock, called muck, backward through the machine and out of the tunnel. At peak operation, the TBMs were removing over 1,000 tons of rock per day. But the rock was not always cooperative. In several sections, the rock under extreme pressure was so hard that it shattered the steel cutting teeth within hours. TBMs that were designed to advance 40 meters per day slowed to single-digit meters, sometimes less. In other sections, pressurized underground water broke through without warning, flooding sections of the tunnel and forcing emergency responses that could delay progress by weeks. The TBMs were not just machines. They were the front line of a war against the mountain. And the mountain pushed back. Nothing about the geology of the Gotthard Massif made this project easy. The tunnel passed through 15 distinct geological formations over its 35-mile length. Each one required different engineering approaches, different support systems, different safety protocols. The Tavich Intermediate Massif, a zone of heavily faulted and fractured rock, presented some of the most extreme challenges. In this zone, the rock had been so stressed by millions of years of geological movement that it behaved almost like a liquid under the pressures encountered at depth. It oozed. It crept. It pressed inward on the tunnel walls with forces that could crush steel reinforcement. Engineers called this phenomenon rock burst, the sudden, violent release of stored energy in highly stressed rock. Without warning, sections of tunnel wall would explode inward, sending rock fragments flying at lethal velocities. Workers in those sections had to wear heavy protective gear at all times and maintain constant vigilance for the sounds that preceded a burst. In other zones, the rock temperature reached 46 degrees Celsius, 115 Fahrenheit, from geothermal heat deep in the Earth's crust. Workers operated in conditions that would shut down any normal construction site. The engineering response was continuous adaptation. Where rock was hard and stable, the TBMs advanced rapidly. Where rock was fractured or pressurized, workers switched to conventional drill and blast methods, slower, more controlled, more adaptable to the specific conditions of each section. In total, the tunnel passed through rock of every conceivable type, and each type demanded a different solution. At its peak, the Gotthard Base Tunnel project employed over 2,400 workers simultaneously. They came from across Europe and beyond. Swiss engineers and managers, Italian, Austrian, German, and Portuguese construction workers, geologists, surveyors, concrete specialists, electrical engineers, ventilation technicians, and they worked underground. The logistics of operating a construction site 35 miles inside a mountain are staggering. Workers couldn't simply drive to the work face. They traveled by electric locomotive, riding small trains deep into the tunnel to reach their workstations. The journey from the entrance to the active construction phase could take over 30 minutes each way. Shifts ran continuously, 24 hours a day, 365 days a year. At no point in the 17-year construction period did work stop entirely. The mountain was always being drilled. The conditions were extreme. Heat from the rock, noise from the machines, dust from the drilling, the constant psychological weight of working under thousands of feet of mountain. Safety systems were comprehensive. Ventilation was engineered to maintain breathable air throughout the tunnel. Emergency refuges, pressurized chambers stocked with oxygen, water, and first aid, were spaced at regular intervals along the tunnel. Despite all precautions, 2 workers died during construction. Their names are recorded on a memorial at the Gotthard Tunnel entrance. Every other person who worked in that mountain came out alive. On October 15th, 2010, something happened that Swiss engineers had been working toward for 14 years. The final rock barrier, a section just a few meters thick separating the two advancing tunnel faces, was blasted away. The tunnel broke through. Workers on both sides, who had been drilling toward each other for years from opposite ends of the Alps, met in the middle of a mountain for the first time. The precision of that meeting was extraordinary. The two tunnel faces, advancing from the north portal near Erstfeld and the south portal near Bodio, had to meet within millimeters of alignment. Despite being separated by 35 miles of rock, multiple geological formations, underground water, and years of accumulated measurement error, the actual alignment error at breakthrough, 8 centimeters horizontally, 1 centimeter vertically, over 35 miles of mountain. That precision, achieved using GPS survey systems adapted for underground use, laser alignment tools, and continuous geological monitoring, represented one of the greatest survey achievements in the history of civil engineering. The workers who had driven those tunnels toward each other shook hands through the breakthrough hole before it was even large enough to step through. Boring the tunnel was only the beginning. Once the TBMs had passed through a section of rock, a construction process of almost equal complexity began behind them. The raw tunnel bored by the TBM was a rough, circular hole in rock. To become a functional railway tunnel capable of carrying high-speed trains at 250 kilometers per hour, it had to be transformed completely. First, a concrete invert, the tunnel floor, was poured, creating a flat, level surface. Then, a waterproofing membrane was applied to the entire tunnel circumference, protecting the structure from groundwater. Then, a secondary concrete lining, the final inner shell, was cast in place, creating the smooth, finished tunnel you see when you travel through it. Inside that finished tunnel, engineers installed the rail infrastructure, concrete sleepers, rail tracks, electrical catenary systems, signaling and communication cables, drainage systems, emergency walkways, and cross passages connecting the two parallel tunnel tubes every 325 meters. The ventilation system alone is a masterpiece of engineering. The tunnel must be able to clear smoke from a fire within minutes, in a 35-mile enclosed tube at depth, while maintaining safe conditions for evacuation. Multiple ventilation shafts and a sophisticated pressure control system make this possible. The safety systems embedded in the tunnel represent decades of railway safety research applied to an environment that had never existed before. It took 5 years after the breakthrough to finish the interior and prepare the tunnel for testing. On June 1, 2016, the Gotthard Base Tunnel opened for freight traffic. On December 11, 2016, it opened for passenger trains. The numbers are immediate and dramatic. Travel time between Zurich and Milan, two of Europe's great financial and economic centers, dropped from 3 hours 40 minutes to 2 hours 40 minutes. A full hour saved on a journey that crosses the Alps. Freight capacity through the Swiss Alps increased by 50%, without adding a single truck to the mountain roads. The Swiss Federal Railways projected that the tunnel would shift 1 million heavy truck journeys per year from alpine roads to railway. The reduction in alpine truck traffic, in diesel exhaust, in road damage, in noise for mountain villages, was immediate. The economics were transformative. The Gotthard Base Tunnel turned Switzerland from a geographic obstacle into a competitive advantage. Goods moving between Rotterdam and Genoa, between the North Sea and the Mediterranean, now move faster through Switzerland than around it. In its first full year of operation, the Gotthard Base Tunnel handled over 13,000 train movements. The mountain that divided northern and southern Europe for centuries crossed in under 20 minutes. The Gotthard Base Tunnel is more than a tunnel. It is a demonstration, at a scale that cannot be ignored, of what sustained national will and engineering excellence can achieve against the most formidable natural obstacles on Earth. Switzerland is not a large country. It is not a superpower. It does not have vast natural resources or an enormous industrial base. What it has is precision, patience, and a democratic tradition of making long-term decisions. 17 years of construction funded by a public vote that most nations find impossible. The engineering techniques developed for the Gotthard, the geological modeling, the TBM management in extreme conditions, the underground survey precision, the safety systems for high-speed rail and deep tunnels are now being applied to tunnel projects from Norway to Australia. When Chile plans tunnels through the Andes, when India considers railway connections through the Himalayas, when any nation looks at a mountain range that stands between it and something it needs, engineers study what Switzerland did under the Gotthard. The tunnel will operate for at least 100 years, perhaps longer. The concrete that lines it, designed to withstand the pressures of 1.4 miles of overburden indefinitely, will outlast the engineers who designed it, the workers who poured it, and the political structures that funded it. Deep under the Alps, in the dark, trains move through rock that was solid for 60 million years, and will be for 60 million more. If you take a train through the Gotthard Base Tunnel today, if you board at Zurich and sit back and watch the entrance approach, something strange happens. The mountain swallows you. The daylight disappears. The walls close in. And for the next 17 minutes, you travel through solid rock at 250 kilometers per hour, a mile and a half below the surface of the Alps. You are in the deepest, longest railway tunnel ever built. And it feels like nothing. Smooth, quiet, climate-controlled. You might check your phone. You might order a coffee. You will almost certainly not think about the 7,500 feet of mountain above your head. You will not think about the 17 years of work, the 2,400 workers, the $12.5 billion, the two men whose names are on a memorial at the entrance. You will arrive in Italy, or you will arrive in Switzerland, and you will collect your luggage and go about your day. And that is the measure of what was achieved here. Not the records, not the statistics, not the engineering superlatives, but the fact that crossing the Alps, something that once took days, that once killed travelers in winter storms, that once shut down trade routes for months, now feels like nothing at all. The greatest engineering achievements always disappear into the ordinary and leave the world changed.